Greetings, and thank you for attending this presentation of the SAE World Congress. My name is Dylan Brown, and I'll be jointly presenting today with my co-author, Zhou Zhao. Here we'll be detailing our development of a novel methodology, Dyno-in-the-Loop, as a platform for testing connected vehicle applications. We'll first describe the system architecture, then discuss the hardware platform setup, and finally, we'll consider a case study. In a collaborative effort with Oak Ridge National Laboratory and US Hybrid, as part of the Department of Energy's ARPA-E Next Car program, UC Riverside developed a plug-in hybrid electric transit bus and evaluated its performance with this Dyno-in-the-Loop methodology. Connectivity, automation, shared mobility, and electrification. We see these technologies in development and understand that these have the potential to improve our performance on every metric listed on the right. How, though, can we quantify the system-level impacts of these new technologies? CAVs, EVs, and new shared mobility applications interact in complex ways. Our Dyno-in-the-Loop methodology allows us to evaluate these interactions in a controlled environment. With a mixed reality simulation, we seek to balance model accuracy and scalability in our environmental impact analysis. The current state-of-the-art for testing with respect to CAVs and environmental impact involves a combination of microscopic traffic simulation, vehicle and powertrain simulation, and finally, real-world testing. Each of these approaches, performed independently of the others, has some particular drawbacks. Public road testing of V2X connected signals, for example, is limited to geographic locations where this infrastructure has been installed. Testing which takes into account these CAV technologies can be performed in a more immersive multi-resolution simulation environment. For example, the figure below shows a combination of the Sumo urban mobility simulation on the right and the Unity game engine on the left. However, these tools are heavily reliant on model accuracy. Some highly developed testing facilities combine the fidelity of real-world testing with the immersive connectivity of a CAV simulation environment. For example, the University of Michigan's M-City Lab is used here in concert with PTV's VISA. Engineers get the best of both worlds, but are limited by the cost of testing time on the proving ground. Often, the ceremony of scheduling time on the test track can get in the way of rapid design iteration. Our approach and contribution is the development of a test platform which allowed us to bring our full vehicle hardware into the simulation loop while keeping the test budget within reason. With our heavy-duty chassis dynamometer lab on campus, we were able to test our transit bus's hybrid powertrain in a simulated environment using this Dyno-in-the-Loop configuration. We can configure the simulation for multiple roadway networks and traffic scenarios. I'll leave it now to Zhou Zhao to discuss how our system architecture leverages this mixed reality approach.
Hi, this is Zhou Zhao. This slide shows the general system architecture of the proposed Dyno-in-the-Loop development and testing platform, which basically consists of a physical world and a simulation world, with the communication device or module being the connection between two worlds. In the physical world are the chassis dynamometer and the test vehicle. The major component in the chassis dynamometer including roller, load absorber, power supplier, and the monitoring and control system. On the test vehicle are data acquisition system and the onboard computer. The onboard computer can process the information retrieved from the CAN bus and send control signals back if any real-time automatic powertrain control algorithm is running. For advanced driver assistance system testing, the driver can follow the advisory information delivered through the driver vehicle interface, or DVI. As to the simulation world, using the API, the information of the test vehicle and the chassis dyno can be transmitted to the macroscopic traffic simulator. In the simulator, a virtual counterpart of the test vehicle is synchronized in terms of the vehicle dynamics. The simulation engine governs the operation of, first, other road users like surrounding vehicles and pedestrians, and second, the traffic control modules, like the traffic signals. Then the system-level performance can be evaluated with the embedded functions or user-defined plugins. Following the proposed system architecture, vehicle dynamics control with driver assistance can be tested through the framework shown in this slide. Interacting with the simulation environment, the vehicle dynamics optimization module can calculate the advisory speed profile and then delivers it to the test driver via the driver vehicle interface. For the automatic powertrain control testing, The powertrain control module replaces the driver and the driver vehicle interface through the onboard computer, transferring the advisory speed profile to the detailed powertrain command, like the required engine torque and motor torque. Besides the aforementioned applications, the Dyno-in-the-Loop platform is open and flexible enough to have many more extensions. For example, it is possible to fuse other elements to the system, such as wireless communication devices or communication network simulation environments, portable traffic control devices, or signal control emulators, and charging stations or corresponding simulators. Also, we can include the existing resources or even the resources from different laboratories or test sites into the system. It can support collective testing effort on the system development and evaluation in a common mixed reality environment.
Thanks, Joe Chow. I'll now take a few moments to describe the specific hardware of our Dyno-in-the-Loop platform as implemented at UC Riverside. The Center for Environmental Research and Technology, or CSERT, at UCR, operates a chassis dynamometer laboratory for heavy-duty vehicles. On this Mustang dynamometer, we installed the plug-in hybrid electric bus, or PHEB. This was a CNG NABI transit bus converted to hybrid by US Hybrid in Torrance, California. US Hybrid additionally provided us with a CAN-based interface for direct powertrain and power split control. We used vector hardware and tools such as Canalizer to transmit motor torque commands to the bus. Closing the loop, live data such as vehicle speed could be fed back into VISM via its API. The PHEB may look a bit odd with its 51-inch frame extension, but this is to accommodate the electric motor in the driveline. It also makes it somewhat tricky, but not impossible, to navigate in a tight parking lot. We can typically test for about 2 days in the configuration shown before needing to remove the bus to refuel. This slide shows the hardware components for the CAV applications under test. Specifically, we'll need forward range radar, DSRC for vehicle-to-infrastructure communication, a driver's aid for speed recommendation, and a data acquisition system. Shown here is an example interface, including some of the information that could be shown to a driver, such as distance to the next intersection, time remaining in the signal phase, and preceding vehicle range. We worked closely with our colleagues from Oak Ridge National Labs to develop a Simulink model-based control system for the PHEB. If the bus fails to receive a control message from us via CAN within an agreed-upon deadline, the bus will fall back to onboard control. However, with the Simulink real-time kernel driver, we're able to meet this deadline with Simulink in the control loop on our Windows development PC. Here we have a video to nicely summarize the project. Bringing together all the components of the Dyno-in-the-Loop platform, this slide shows the resulting integrated testing environment. The driver sees the first-person simulation view ahead in the upper left. The bus itself is driving on the chassis dynamometer, upper right, in sync with the simulation. In the center, we have the driver's aid interface. And finally, along the bottom, we show a bird's-eye visualization of the VISM traffic network.
To prove the concept and validate the effectiveness of the proposed Dyno-in-the-Loop platform, we test and evaluate an innovative connected eco-operation system for the efficient plug-in hybrid electric bus, or PHEBs. Taking advantage of the CAV technology, this system performs the optimization of the vehicle dynamics to reduce the energy consumption and tailpipe emissions of the target PHEB. More specifically, the system integrates 3 CAV applications: eco-stop, eco-cruise, and eco-approach and departures. The test is conducted with driver assistance. We first coded a real-world traffic network with 3-mile signalized corridor on the macroscopic simulator PTV VISM. The corridor contains 7 signalized intersections and 7 bus stops. Then the information of other road users, traffic controller, and road network are simulated and transmitted from the simulation engine. With the knowledge of the bus stop location, signal phase and timing, and real-time traffic conditions, the most energy-efficient longitudinal speed profile is calculated by the vehicle dynamic optimization algorithm. Finally, the test driver is provided an optimal advisory speed shown on the driver vehicle interface. This slide briefly introduces the optimization algorithm. Firstly, we discretize the time and space, considering the physical constraint, such as maximum or minimum acceleration. All possible routes in terms of time and space are connected from nodes to nodes. Then the energy cost between two nodes are estimated. Finally, we applied Dijkstra algorithm to solve this single-source shortest path problem with non-negative cost. The figure shows an example speed profile calculated by the optimizer. The blue line shows the baseline speed, whereas the orange dashed line shows the optimal speed. Due to the availability of the downstream traffic information via connected vehicle technologies, the PHEB is able to avoid coming to a full stop in many situations. We have conducted a series of tests at 5 different traffic congestion levels, and the table in this slide summarizes the results of energy savings. The overall energy consumption is the equivalent battery energy consumption, combine the real battery energy consumption and the fill rate, considering the energy efficiency. As can be observed from the table, we achieve energy saving for all congestion levels. It should be noted that these energy savings are a result of vehicle dynamic optimization only, and greater benefits are expected when the powertrain control optimization is combined. To sum up, in this research, we proposed an innovative hardware-in-the-loop development and testing platform for modeling and evaluation of emerging transportation technologies. The key components for this platform include dynamometer, test vehicle, driver vehicle interface, socket and API for connection between the physical world and simulation world, and finally, the simulation engine that governs the operation of other road users and the traffic control modules. Also, we have conducted a case study to illustrate the configuration of the platform. Compared to the pure numerical or traffic simulation approaches, the proposed platform can provide higher fidelity results and further insight into the system performance when deploying in the real-world environment. Compared to other X-in-the-loop or real-world road test approaches, the proposed platform is more flexible in different traffic scenarios and cost-effective. This research is supported by the U.S. Department of Energy under the ARPA-E Next Car program. We would also like to thank to the colleagues from UC Riverside, Oak Ridge National Laboratory, and US Hybrid for their strong support and constructive comments for the Dyno-in-the-Loop testing. That's it for the presentation. If you have any questions or comments, please feel free to contact us. Thank you.